In this video, we are finally going to construct the quotient ring R mod I, where I is an ideal of the ring R. All right, so let's let R be a ring, and let I be an ideal of R. Okay, so then the quotient ring R mod I, and that's how we pronounce it, R mod I, is the set of additive cosets of I in R under the following operations. And here are the operations. If I have two cosets, A plus I and B plus I, then I define their sum as just A plus B plus I. So I'm adding together two cosets, this one, and I'm getting one new coset, which is this one. And I'm just adding the two coset representatives together. All right, and then the operation of multiplication is defined by A plus I times B plus I equals AB plus I. Which I guess when you look at it in terms of the distributive property seems kind of weird. Like, we're used to multiplying binomials and we do not get AB plus I when we do that. So, I mean, what is a possible reason to be satisfied with this? Not that this is a proof of anything. It's just more of a reflection on what we're doing here. But if I were to multiply those as though they were binomials, they're not exactly. But I would get AB plus AI plus IB plus I times I. And one thing we can see there is because I is an ideal, it absorbs multiplication. So what I have here, it may not be exactly the entire set I, but certainly everything here belongs to I, because I'm just taking elements of I and multiplying by something in the ring. And same here, everything here is going to be an I, and certainly everything in here is going to be an I, because multiplying two ideal elements gives me an ideal element. So in a way, I can think of this as AB plus something that belongs to I. Okay, not that that makes this right or wrong, it's just this is a definition. Okay, we can define things however we want as long as they end up working in the way that we wish for them to work. But anyway, that's the definition of the quotient ring. It is the set of cosets of I under these two operations. Okay, but now there is a job that we have to do because, and I'm going to illustrate this using an example. If I'm in Z, and let's say that my ideal is the set of all even integers. Okay, then, well, this is one of the cosets, 0 plus I. That's actually the ideal itself. And that consists of all the even integers. But then I could also call that coset, I don't know, I could call it 4 plus I. And that would also be the set of all evens. It's exactly the same coset. Okay, so this coset has two different names. In fact, it has a lot of different names. Those are just two of them. And then I have this other coset, 1 plus I, which is the set of all odds. And I have other ways of calling that coset, like I could call that negative 7 plus I, and it'd be exactly the same set. And the reason I'm bringing this up is when I define these operations of addition and multiplication, these definitions appear to be name dependent. In other words, when I'm adding the coset A plus I and B plus I, the result depends very much on what A is and what B is. Or at least it appears to depend. We have to prove that it doesn't really depend all that much. Similarly with multiplication, the result I get, AB plus I, well, it appears to depend on what my A and B are. In other words, if I were to multiply these two cosets, this one with this one, well, I could multiply these, and my result would be 0 times 1 plus I, and that's 0 plus I. Or I could multiply these, which would be the same two cosets under very different names, and my result would be 4 times negative 7 plus I, or negative 28 plus I. And it turns out those are the same because 0 and negative 28 are both representatives of the same coset. They're both even. But I have to prove that in general, I must prove that these operations are well defined. In other words, I don't get different results by operating on the same cosets with different names. In other words, if I use different names for the same cosets, I will still get the same results in the end, maybe just by a different name. Okay, so I need to prove these operations are well defined. Okay, so what does it mean to do that exactly? Well, I need to prove that if a1 plus I is equal to a2 plus I, and b1 plus I is equal to b2 plus I, so in other words, two cosets each by two different names, then a1 plus I plus a2 plus I, sorry, b1 plus I, there we go, that's equal to a2 plus I plus b2 plus I. In other words, replacing these with different names for the same things doesn't change the results. And also I will need to prove that a1 plus I times b1 plus I, that's the same as a2 plus I times b2 plus I. Alright, so here's the proof. By the way, one thing I'm going to do in this proof is I'm going to use additive cosets and congruence classes interchangeably, because I've proven in a previous video that those are exactly the same thing. And I should take this opportunity as well to just state the definition of quotient ring in terms of congruence classes. I think I'll do it in the same frame here. I was thinking about whether to do it here or someplace else. But let's just add here, this is the same as the congruence classes mod I. So if you want to think about the quotient ring in terms of congruence classes rather than additive cosets, there is nothing lost by doing that. And also the definition of the operations, it changes its look a little bit, but it's really the same idea. So the definition in terms of congruence classes is if I add the class of A and the class of B, I get the class of A plus B. Because we showed in a previous video that the coset A plus I is the same as the congruence class of A modulo I. And then class of A times class of B equals the class of A times B. Okay, so that's the definition in terms of congruence classes. And like I said, I'm going to use the idea of congruence and congruence classes to prove that these operations are well defined. All right, so here's the proof. So let's assume that a1 plus I is equal to a2 plus I, and b1 plus I is equal to b2 plus I. Okay, so what does that mean? Well, I'm going to restate this in terms of congruence. So this means that a1 is congruent to a2 mod I, and b1 is congruent to b2 mod I. All right, and then let's state that in terms of what congruence means. This means that there exist, let's call them x and y, both belonging to the ideal, such that a1 plus x is equal to a2, and b1 plus y is equal to b2. So now I'm going to try and use these facts to prove that, we'll do addition first, that a1 plus b1 is congruent to a2 plus b2, because I already know that according to my definition, what I'm trying to show here is that a1 plus b1 plus I has to be the same as a2 plus b2 plus I. And then down here I'm trying to show that a1 b1 plus I is equal to a2 b2 plus I. So these are just restatements of what I need to prove. All right, so let's first work on addition here. We know that a2 plus b2, just using substitution, that's equal to a1 plus x plus b1 plus y. And then rearranging, using the commutative and associative properties, that's the same as a1 plus b1 plus x plus y. And you should look at that and say, ah, that looks like something that belongs to my ideal, because x and y both belong to I. And that means that I've written a2 plus b2 as the sum of a1 plus b1 and an ideal element. That means that a1 plus b1 is congruent modulo I to a2 plus b2. So that means that a1 plus b1 is the same class as a2 plus b2. Those congruent classes are the same, therefore addition is well defined. Great. What about multiplication? That one's a little bit trickier, but here is where we use that key property of an ideal, that ideals absorb multiplication. Okay, so I'm going to continue using these facts here. These didn't go out of scope when I finished the addition argument here. So we also have a2 b2 equals a1 plus x times b1 plus y. And now I will multiply those like binomials because that's what they are. a1 b1 plus a1y plus xb1 plus xy. And what do I have there? I know that y belongs to my ideal, and I absorbs multiplication, so that whole thing belongs to I. Similarly, x belongs to I, and I absorbs multiplication, so that also belongs to I. And finally, the product of any two elements of I also belongs to I, which means this whole sum here belongs to I. Therefore, a2, b2, or let's write it this way, a1, b1 is congruent to a2, b2 mod I. So these two classes, the class of a1, b1 and the class of a2, b2, are exactly the same. So that means multiplication is also well defined. So just to recap, the problem that we were trying to solve here was we've defined an operation or a function, as we often do in algebra, by using representatives of a set. Anytime we do that, we have to make sure it doesn't matter which representative we select. So the conundrum we were trying to resolve here was we were trying to show that, for example, multiplying these two elements of z mod I, this is from our example over here, multiplying these elements of z mod I is the same as multiplying these elements of z mod I, because after all, they're exactly the same elements. We're just calling them differently on the left versus on the right. On the left, we would have gotten 0 plus I. On the right, we would have gotten negative 28 plus I. And if those end up being different things, then our multiplication isn't really an operation at all, because it's an operation on names of things rather than on objects. But it does turn out these are the same, and this argument down here illustrates why they're the same. Alternatively, you can think about multiplying these out and just saying, well, 4 was equal to 0 plus something in the ideal, negative 7 was 1 plus something in the ideal, and we multiply that out, we see that all those little extras end up getting absorbed into the ideal. So they don't affect which coset we're in. That's sort of the synopsis of what's happening in this argument. So anyway, we do have a quotient ring. Its operations are well defined. You can rest easy at night knowing that. And just as a way of wrapping up, let's go ahead and check on that claim that we made in a previous video that z mod I is isomorphic to z mod 2. So is that true? We can actually verify that now because we can construct addition and multiplication tables for z mod I. And I'm going to do this using the congruence class language with the brackets rather than coset language, just because brackets are easier to write and a little bit more compact. So making an addition table, we'll have 0 and 1 over here, 0 and 1 down here. And again, those are the only elements of this quotient ring because there's only 2 different cosets needed to make up all of the integers. Anyway, when we add, we're just adding congruence class representatives. So we're adding 0 plus 0 and get 0, add 0 and 1 to get 1. Same here. And then 1 and 1 gives me 2, so I could call that brackets 2. But I know that 2 is congruent to 0 modulo the ideal, so this is really 0 again. And that does look an awful lot like addition in z mod 2. I can also do a multiplication table. We do need to check that both operations behave exactly the same as in z mod 2, not just one of them. But again, I have 0 times 0 is 0, 0 times 1 also 0, same here, and then 1 times 1 is 1. So this really is addition and multiplication in z mod 2. These behave exactly the same. So I could have called these, I could have called the class of 0 what we usually call 0 in z mod 2, and the congruence class of 1 is what we call 1 in z mod 2. In fact, if we're being really technical when we talk about z mod 2, these congruence classes are exactly what we're talking about. There's really no difference in how this is technically constructed versus how this is technically constructed. In fact, you could go on and say these are not only isomorphic, they're really exactly the same thing conceptually.